Yeah, thanks for the introduction. Thanks everyone for being here, for taking the time to visit my presentation. So I don't think Hassan will be here. I think he was quite busy today. But yeah, so as George said, I'm currently visiting McGill. I'm a second-year PhD student at the University of Groningen, and as you expect, I'm interested in dynamic games applied to environmental and resource economics. So what I'll be talking about today is basically the first chapter of my dissertation, which has seen some versions. Maybe some of you have also seen it at the workshop in Paris. So there's still maybe some work to be done, but I think the shape it's entering quite a good shape right now. So let's see. I need to remove myself a little bit. Yeah. So this is a paper about climate change, and specifically about let's say the long-run climate policy. So we are aware that anthropogenic carbon emissions, they warm up the planet, and in turn they damage the environment. So these are often thought of as kind of gradual damages. More recent concerns are about, let's say, crossing irreversible thresholds, and also in turn inducing regime shifts. So that was first documented by Lenton and others in 2008. These days also yearly reports are coming out about basically the status of environmental systems in relation with these kind of regime shifts. So the example that I have in mind for this specific paper is about well, the acceleration of loss of ice sheets, which will accelerate sea level rise, and this is deemed to be plausible after, let's say, 2-degree rise in global temperature relative to pre-industrial levels. And of course, these kind of the sea level rise will be accompanied with associated loss of welfare to society. And the question that I'm interested in here is how to respond to such looming regime shift or disaster, so to say. So I consider two instruments. So the first is mitigation, which is that countries, they reduce their emissions to reduce the hazard of such an event or such a shift from a state of high environmental quality to a state of low environmental quality, to reduce the likelihood of that taking place. And that can be thought of as a global type of instrument, right? Alternatively, countries can also resort to adaptation, right? So they proactively invest in adaptive capital to make sure that once these kind of events takes place, the impact and the associated welfare loss will be lower. So these are two instruments that I consider. This paper does not, that's good to mention, this paper does not necessarily consider geoengineering or any kind of carbon capture storage. Because I think already the model is complicated enough. And also this kind of geoengineering has very similar features to climate mitigation in terms of public good spillovers. It's something worth looking into for the future, but I think for now, this will be it. So when we think about how to respond to these kind of possible future disaster events or regime shifts, yeah, we have these instruments, mitigation, adaptation, and the trade-off between the two was studied by Zemmel in his 2015 JETSI paper. And there he studies how a single decision maker might allow for a risk impact trade-off. So basically, if we have a single decision maker or a social planner, that will choose just the optimal allocation between the two instruments. In case of a single decision maker, there's not a real distinction in terms of public good kind of spillovers, because well, we are considering a single decision maker. So a natural extension, I thought, would just be to see how his framework, his ideas relate to a scenario where we have multiple decision makers, which I think will be, which I call countries in this paper, how that trade-off is affected when we have these multiple decision makers that might not cooperate. And it turns out that this cooperation is quite important, right? So if countries are cooperating in their climate policies, then we go back to this ZEML style model where we have different climate policy instruments that will complement each other. And in this case, the option to adapt will increase welfare. Increase of non-cooperation, it's slightly different. Adaptation that gives countries more incentive to free ride in their pollution control, and in return, that lowers the social welfare overall. And the idea is, well, maybe so the idea is basically, so if a private good becomes available, that crowds out contributions to the public good. In this case, that actually is welfare decreasing. So just to give a quick overview of how this relates to the related literature. So I think it's quite nice with this paper that I can touch upon 3 strands of literatures. So the first is this strand of literature which considers endogenous regime shifts or disasters, which is mostly dominated by Zür and Semmel. And second strand of literature is basically about the trade-off between mitigation and adaptation. Right, so we have contributions by Burchett, and also Zemmel is Jetsy paper, and Van der Ploeg and de Zeeuw is also quite an important one. And the third strand is basically the one where I contribute to the non-cooperative pollution control games, right? So they started out by Van der Ploeg and de Zeeuw and Dogner and Long in the 90s of the previous century. These days also people are interested in extending that model with regime shifts, so that is kind of the contribution of Sakamoto, but also Nikuya, Wagner and de Zeeuw. And it's also quite nice that I touch upon Vardar and Sakur, who also studied to some extent the trade-off between mitigation and adaptation, but more in response to gradual climate damages, right? So my contribution in that sense is that I can study these strategic and welfare effects of the mitigation adaptation trade-off in the presence of non-cooperation. And also a large part of the paper is methodological, right? So we show how to handle multiple state variables and regime shifts, and how to solve the resulting equilibrium, which is not straightforward. Okay, so how do we get there? So we analyze a model that features the problem of transboundary pollution under cooperation and non-cooperation. This model features both gradual and abrupt climate damages. And there's uncertainty over the timing of when these abrupt climate damages will be incurred. And then we allow for the possibility of mitigation and proactive adaptation in response to these abrupt climate damages. So what does the model look like? So I base it on the 2-country transboundary pollution game by Van der Ploeg and de Zeeuw. And basically, the main features are how to model mitigation and adaptation, right? So mitigation basically entails in this case that countries, they lower their emissions to lower the pollution stock P, right? So lower emissions relative to business as usual, and pollution stock follows these linear dynamics. So emissions are indexed by E, and emissions by countries are indexed by I, and so we're doing continuous time. Yeah, this is kind of a straightforward way to write it. And delta, of course, is the depreciation factor. So mitigation that affects the global pollution stock, and what the role that global pollution stock plays in this model is that it determines the occurrence of a irreversible regime shift at a random time, capital T. And we model this as driven by a endogenous hazard rate, right? So it has some exogenous component gamma and then lambda times PT. And basically, sorry, one second. Yes. So the interpretation is basically that if you multiply this h of p with delta t, then you get some kind of probability. And you can use this hazard rate to also derive the cumulative distribution function of this time of occurrence capital T. So if you mitigate, that effectively reduces the pushes forward the arrival time of the expected arrival time of the regime shift. And the second instrument that I consider is local adaptation. And we model this as proactive. So countries can invest I into their own local capital stock KI before time capital T. So before time capital T, countries, they invest, they increase their capital stock to basically brace for impact, so to say. And since we consider proactive investments, we consider irreversible regime shift, and we assume that this damage incurred due to the regime shift materializes right away. There is no need for investments after the regime shift has taken place by assumption. And so capital determines the welfare loss that you incur at time capital T. So at time T, there's a loss of welfare psi in each country, and how high this welfare loss is basically determined by how much you mitigate, so, how much you adapt, sorry. So adaptation determines the size of the impact, and mitigation basically can be used to affect the timing. Right, and so in response to such a regime shift, countries, they can lower their emissions, mitigation, which is global, or they can invest in their local adaptive capital stock. And so, this kind of model formulation very conveniently allows for splitting up the time horizon. So basically, we consider an infinite horizon problem, and we split that up into two periods. Right, a pre and a post-shift regime, which is these terms I will use throughout this presentation. So the post-shift objective, which basically starts at time capital T and goes to infinity, has a very simple structure. So there are no capital investments anymore, and the size of the shock is fixed. So then basically the objective is this integral from T up to infinity. We discount at a constant rate rho. And countries, they get some utility from their emissions, but they also suffer from these gradual damages. And then this objective is shifted downward by how much you adapt, basically, because this psi term captures this loss of welfare due to the regime shift. And splitting the problem up into these kind of two regimes is quite convenient. Because we can also write down an objective function for the pre-shift regime. So Ji of B, that will be the objective of country I before the regime shift has taken place. And it has two components. So the first line over here, that basically captures the payoff stream up to time capital T, right? So again, we discount at constant rate rho, and then we have some utility from emissions, investment cost, right? Investing into adaptive capital that is costly. And then we suffer from these gradual damages. And once we arrive at time capital T, we jump to this second regime. And there we have this loss of welfare. And the objective we defined before, right? JIA, that is the objective for country I after the regime shift has taken place. And then we need to take expectations. because we do not know exactly when this time capital T is going to take place. We know its distribution, but yeah, we need to account for that. So we can basically split up the problem into two long periods, and that makes analyzing it slightly easier. So we impose some functional forms, which are mostly linear quadratic, which is to some extent in line with what people do in these kind of differential games, right? So we have some linear gains from emissions. This would be kind of a cost of producing emissions, non-climate related. Then investment costs are linear quadratic. Gradual climate damages are quadratic, and this welfare loss associated with the regime shift, that kind of, I borrowed that from Zemmel. So the interpretation is that basically this capital AI that determines the maximum welfare loss that you can attain, and Z measures some adaptation efficiency, right? So if KI, if your capital stock reaches the level ZI, then you incur half of the maximum climate damages. And if K is equal to 0, then of course you don't adapt at all. The maximum damage that you can incur is AI. And so in solving this model, we consider two outcomes. So we do everything symmetrically in terms of parameters, and we consider the cooperative outcome, so the first best, and then we also have a non-cooperative outcome where we focus on the Markov Perfect Nash Equilibrium. And our benchmark is, so then we compare these outcomes in a model where countries, they have access to climate mitigation, climate adaptation, to a benchmark where countries either cooperate or not, and they cannot adapt. And in that way, we can study the role that adaptation has in affecting
Excuse
incentives
me,
to.
I have a small question.
Mm-hmm.
I have a small question regarding the second regime, actually the post shift. What happens? The delta in the pollution accumulation equation becomes 0, or still there is absorption by nature? As the Intavonen-Witthagen original model, maybe?
No, so basically this is in the way that I model these kind of regime shifts. The only thing that the regime shift does is that it gives countries some extra welfare loss, right? So it doesn't affect the state dynamics in any way. It doesn't give some kind of shift in a parameter, as in the QEI, for instance, does, or it doesn't shift up the damage parameter. So that's it basically. So it's quite
the dynamics remains the same.
Yeah.
Okay.
Yeah.
Thank you.
So it is a slightly simplified way to maybe account for this this welfare loss, but it is kind of one of the most tractable ways to do it, I think. But thanks for your question. So,
Can I ask you something?
Yeah, sure.
So if I recall, I was just wondering if you could elaborate a bit more on the dynamics for capital. So we have like this after the disaster time capital T, you have this adaptive capital, and then it becomes, you don't invest anymore, right? I was wondering if is there any other kind of capital, like, I don't know, like that helps mitigating climate change, or there is only one unique type of capital that is before the big change, and after that we cannot build anything else?
Yeah, so this is no, so the only role that there's only one type of capital in this model, and that is capital that plays the role of basically lowering this impact of disaster. So there's no either any kind of capital that basically allows for for anything else. No.
Okay, thank you.
So where was I? Yeah, okay. So we solve both a cooperative and non-cooperative outcome, and then we compare this to a case where adaptation is not possible. So first, let's see what the cooperative outcome looks like. Right, so we have these two regimes, and we use continuous time dynamic programming to solve this, and we start in the second regime, so basically working backwards. So what we can do is basically define a value function after the regime shift has taken place, VA in a cooperative outcome superscript C, and that's basically the maximum welfare that you can attain afterwards in a cooperative outcome, right? So we sum basically over the two objectives. And one thing which we can then do, so since we assume that we are mostly interested in, we are only interested in these proactive investments in anticipation of this regime shift, and we assume that the impact materializes right away. That means that the role of capital after the regime shift is non-existent. So only the level of capital at time capital T is important. And that basically means that we end up back in this Dogner and Long framework, which is convenient because we can solve that analytically, right? So we know that under these kind of assumptions, the value function in a cooperative outcome has this linear quadratic structure, and then we account for this loss of welfare, these psi terms basically. And that's quite convenient to do so, because if we look at the pre-shift value function VB of C, that is quite a complicated expression, because basically it's the maximum welfare that you can attain before the regime shift has occurred. And so again, it has this kind of same structure as the objectives that we defined before. Now we have this value function after the regime shift has taken place. And what we can do is we can write down the corresponding Hamilton-Jacobi-Bellman equation, which is quite hard to solve. So let's take a quick look at what it consists of. So on the left-hand side, we have this rho times the value function. And we have this flow payoffs in the first part of the Hamiltonian of the Hamilton-Jacobi-Bellman equation consists of these flow payoffs. So this is utility from emissions minus investment costs minus gradual damages. Then we have this additional term which appears due to this regime shift structure. That term captures the welfare loss due to the regime shift. And then finally we have the partial derivative. So then we have this partial derivative of the value function with respect to pollution stock times the pollution dynamics. And similarly for the partial derivative of the value function with respect to the two capital stocks times the capital dynamics. So given that we have this kind of two-mode framework, and we have an analytical expression for the value function post-shift, we can write down the corresponding Hamilton-Jacobi-Bellman equation before the regime shift has taken place, and then we solve this numerically, but that's something I will come back to in a second. But yeah, writing the model down in this way makes it at least a bit easier to handle due to this regime shift structure. So let's think about the non-cooperative outcome. So we focus on the Markov Perfect Nash Equilibrium, and I think it's good to mention, given that we had some talks last few weeks by Nico and by Pierre about what kind of equilibria we are considering. So we restrict ourselves to linear strategies post-shift and nonlinear strategies pre-shift. And that is mainly to make the problem at least a bit more tractable, because we know that under linear strategies, we can derive an analytical solution post-shift, right? But a disadvantage could be that, yeah, these kind of assumptions, these restrictions that you impose, they rule out alternative equilibria that possibly could be better in the Pareto sense. I would love to do something about this more rigorously, but I haven't really come up with a way to incorporate this into a framework where we have uncertainty and also where we have multiple state variables. So that is maybe something to look at in the future. So specifically, let's see what the equilibrium looks like. So we have stationary Markovian strategies, as this is an autonomous problem. And these strategies are basically defined for the two different regimes. So in the first regime, where the regime shift has not taken place yet, countries, they decide on their emissions, EI, before, and they decide on their investments, IIB. And so basically what they choose at any time t depends on the state of the system in the Markovian sense. Afterwards, so when we are in the second regime, countries, they only decide on their emissions, EIA, and since this capital is redundant, they only condition their emissions on the pollution stock P of T. And so when we're considering Markovian strategies, we go into continuous time dynamic programming, and specifically here, we due to this regime shift structure, we end up with two sets of Hamilton-Jacobi-Bellman equations that for each regime, we have one set of Hamilton-Jacobi-Bellman equations. And these in each regime pin down the value function and the strategies. So this first set of Hamilton-Jacobi-Bellman equations, that is a set of Hamilton-Jacobi-Bellman equations that correspond to the post-shift regime, and that pins down the value function VIA, so the value function for country I after the regime shift has taken place in the MP, the non-cooperative outcome. So one thing which is convenient, that if you impose linear strategies, that you can solve this analytically. Right, so this is basically what Dockner and Long did. But then we have this additional term which is shifts the value function downward. So with this analytical solution, we basically can move back to the first regime. And that is a bit more complicated. So in this first regime, before the regime shift has taken place, we have two sets of, we have a system of Hamilton-Jacobi-Bellman equations that pin down the value functions. And this is all following basically what Dockner and the others showed in their book. So basically the interpretation of these Hamilton-Jacobi-Bellman equations is very similar to a cooperative outcome, but now the difference is that each country, they maximize the Hamiltonian part of the HDB given the optimal strategy, which is denoted by stars, of the other country. The strategy that results in such a Markovian equilibrium is basically the argument that maximizes the Hamiltonian. And then we use these Hamilton-Jacobi-Bellman equations to give the to obtain the value functions, right? And if we inspect these Hamilton-Jacobi-Bellman equations a bit closer, basically the structure is that the first part of the Hamiltonian part of the Hamilton-Jacobi-Bellman equation has these kind of flow payoffs again. So utility from emissions for country 1 minus investment cost of country 1 minus gradual damages from climate change. Then there is this loss of welfare associated with the regime shift again, the term in red. And then we have basically the partial derivatives of the value function with respect to the relevant state variables times their relevant dynamics. But the main question is, so we can write down these equations following Dockner and Long, but the problem is how to solve them, right? Because if we
may I ask a question?
Yeah, sure.
In the pre-shift problem, you are assuming here that your strategies are time independent?
Yes.
Okay.
Well, so basically this problem is autonomous. So I don't think that is.
But I mean, this part is a finite horizon, something. Anyway, please continue.
That's something I will think about. Yeah, thanks for your point. All right. So the main question is how to solve these Hamilton-Jacobi equations, because we have several state variables which can hint towards the curse of dimensionality, right? And this Hamilton-Jacobi equation is nonlinear, and we have these partial derivatives appearing. And I think one nice feature of this paper is that we try to tackle this problem, specifically these first 2 points. We introduce a method that kind of tackles these points. So to combat this curse of dimensionality, we use sparse grids, which was introduced in the 1960s by Smolyak. Yeah, we follow Judd and others in the implementation of that. And to basically handle this Hamilton-Jacobi equation, we use projection methods combined with implicit updating schemes. One thing which I think is quite nice is that this is, I think, a relatively general method that hopefully can be used also to solve Markovian equilibria in non-tractable differential games, which I think arise quite often in environmental resource economics. But yeah, what does this method look like? So we basically use an iterative scheme. So iterations are labeled K. And so throughout this iterative scheme, we use sparse grids and Chebyshev polynomials to approximate this value function VIB at any iteration K and its derivatives, right? So for instance, at iteration K, we can approximate the value function of country I by means of the product of some basis matrix, which has a low dimensionality, times some unknown collocation factor C. Right, and so this matrix that captures basically the product of polynomials in each direction of the state space. And similarly, we can also capture the derivative of this value function by differentiating these relevant polynomials in a certain direction by means of the product of such a basis matrix times the unknown collocation factor. And so that is basically the approximation part where we try to handle this curse of dimensionality. Then we group controls at every iteration in a factor kappa. And so basically to start this iterative scheme, we initialize some guess for the value function. So we initialize the problem using some guess. And then basically iterations follow this kind of implicit scheme, which I borrow from, let's say, this continuous time finite differences method. So basically, it it's very similar to the Hamilton-Jacobi-Bellman equation that we discussed before, but it has some additional term which kind of resembles what we would have if we were time iterating on a time-dependent Hamilton-Jacobi-Bellman equation. So this is kind of an updating term. And then we have this discount factor plus the hazard rate times the value function at iteration k. And in this updating scheme, on the right-hand side, we have this instantaneous reward given the controls at the previous iteration, plus the gradient of the value function times the state dynamics. And basically, this kind of iterative scheme allows us to express the value function at iteration k, basically in terms of things that we already know because of the previous iteration. Right, and so we have two of these iterative equations. For each country, we have one. And the idea is then that, well, at each iteration, we solve a small system of linear equations. So, and if you solve, you can solve that system of equations within, basically it takes no time. And then you keep on iterating, updating, and after convergence of the algorithm, we can obtain these strategies, the value functions, and the time paths of the cooperative and a non-cooperative outcome. So let's try to see what kind of results follow from this numerical scheme. So before I start showing the figures quickly, adaptation in this case is proactive, which means that all the interaction between mitigation and adaptation is in the pre-shift regime. And so that's also what we will focus on. So in parameterizing this model, basically I follow Nukuya and also Varda and Sakura as much as possible. There's no kind of real world-ish calibration yet. That's something I've been thinking about, but I haven't found the time yet to do that. So we have this base parameterization, and in the paper there are 3 robustness checks for what happens when we lower the discount rate and when we increase the impact of the shock, and also the sensitivity of the hazard rate. Let's see, how am I doing time-wise? Oh, let's see that. Okay. So
still have 10 minutes if you want to leave some time for questions.
Okay, then I've kind of lost track of time. So, but it should be okay. Thank you. So just as a primer, strategies, right? So we in a non-cooperative outcome, as we kind of expect. So first we do emission strategies. So these are emissions of country 1 as a function of pollution stock and capital stock of country 1, keeping the capital stock of country 2 as fixed. So emissions are so pollution stock is on this axis, and capital stock of country 1 is over here. And basically, as we expect, emissions are decreasing in pollution stock, and they are slightly increasing in capital stock. And for investments, the story is reversed, right? So as pollution stock increases, the investments of country 1 will increase, and as capital stock of country 1 increases, its investments will also decrease. So what kind of time path does this induce? Here we have these time paths in the pre-shift regime for a cooperative and a non-cooperative outcome. So on the vertical axis, we have pollution stock. and the horizontal axis as time. And so the blue line has the social planner pollution dynamics, and the red line has the non-cooperative pollution dynamics. And so, as we expect, this non-cooperative outcome is very inefficient in terms of pollution control. We also see that when we're thinking about capital dynamics, right? So on the horizontal axis, again, we have time, but now on the vertical axis, we have capital stock of country 1. And again, the red line has the non-cooperative capital dynamics of country 1, and the blue line has social planner capital dynamics, right? And so we see that apart from some hiccups over here, where in a non-cooperative outcome, countries, they want to first, so in a cooperative outcome, the social planner first wants to build up some capital stock. Basically, the non-cooperative outcome is very inefficient in terms of there's too much capital being built up. And what kind of dynamics does this induce if we try to look at the whole time horizon? So now we have multimodal dynamics. And basically what this figure represents, so we have time on the horizontal axis, we have pollution stock on the vertical axis, and we fix the time of the regime shift taking place. So we fix the capital T at time 40, and then effectively we glue together the dynamics before and after the regime shift has taken place. So the red line is are the pollution dynamics in a non-cooperative outcome in case countries can both mitigate and adapt. And the blue line has the pollution dynamics in case countries do not cooperate and they can only use mitigation in response to climate disaster, right? So we see that at time t, in both cases, the trajectory switches, and they both move towards the same level, steady state level of pollution stock after the regime shift, which is because in our model, capital is only relevant before the regime shift has taken place. But we see that before the regime shift has taken place, the target steady state level of pollution stock is way higher in a case where countries can both mitigate and adapt. And actually, we see that in case of adaptation, almost all of the precautionary motive is taken away by the fact that there's adaptation possible, which I think that kind of hints towards a very high crowding out. So how does this kind of option to adapt affects the hazard, right? So we have now on the horizontal axis, again, time, but on the vertical axis, now we have the cumulative distribution function of the regime shift. So this is a figure for the cooperative social planner outcome. And the red line is the mitigation adaptation scenario, where the social planner can both mitigate and adapt, whereas the blue line is the mitigation scenario. And so we see that, well, if the social planner has more instruments available, it will choose this optimal allocation between the two. And therefore, we see a slight shift of the CDF upwards, but that's not any form of inefficiency. That's only due to the fact that this social planner has more instruments available. And therefore, if it can adapt, it will also mitigate a bit less, and therefore the pollution stock will be higher in a case of a scenario where the social planner can both mitigate and adapt. We also have the same figure, so again, time on the horizontal axis and the CDF on the vertical axis for a non-cooperative outcome again. So the blue line is one where these countries, they only can mitigate, and the red line is one where countries can both mitigate and adapt. And so again, we see quite a steep increase. We see a very steep increase in the CDF, and that is basically due to this inefficiency that arises. So in case of the option to adapt, countries, they will loosen their mitigation policies quite heavily, and there will be more free riding, and in that in turn shifts up the CDF quite heavily, which means that the expected occurrence is also shifted forward. So the expected time of arrival, the regime shift becomes basically earlier. So finally, we touch upon welfare. So we have the time paths of the social welfare pre-shift. This is the cooperative outcome. And again, the blue line is a scenario in which countries mitigate, and the red line is one where countries mitigate and adapt. And we see that in the cooperative outcome, this social welfare shifted upwards. Right, so if a social planner has more instruments that will improve social welfare. In a non-cooperative outcome, we see the opposite pattern, right? So again, the blue line is a scenario where countries can only mitigate, and the red line is one where countries can mitigate and adapt. And in case adaptation becomes present, we saw before that yields a lot of crowding out in terms of contributions to the public good, and that lowers welfare in this model, which I think is quite a so in this case, more instruments do not necessarily improve life if countries do not cooperate. Yeah, and just to conclude, yeah, so this paper was about the trade-off between mitigation and adaptation in a transboundary pollution game where countries either cooperate or not. And basically, this paper touched upon the strategic and welfare effects of the option to adapt, depending on whether countries cooperate or not. We found that under cooperation, yeah, these instruments are complements, but under non-cooperation, that's not the case, and actually, the option to adapt actually lowers welfare. And in the process, we introduced some methods to handle the Markov Perfect Nash Equilibrium in case of a non-tractable pollution game. Yeah, and some future extensions, what I think would be interesting just to think about recurring shocks. So right now, basically, we have a one-time event. But what happens if we are thinking about climate disasters that occur very frequently? Yeah, we could also have asymmetries in timing. And I think one thing which is interesting is to try to touch upon numerical selection of Markov Perfect Nash Equilibrium, equilibria. So right now, we focus on nonlinear strategies, but it could be that other equilibria exist. But that's something figuring out for in the future, I think. Well, that was it from my side.